Good afternoon, everyone. It is a pleasure to introduce the speakers today. It is Vladimir Baulin, who is a new member of our community. Vladimir is currently distinguished researcher at the Beatrice Galindo at University Rovira i Virgili in Tarragona. He started his career in France, where he did his PhD in the University of Grenoble. And then he moved to Strasbourg, still in France, before joining the University of Rovira i Virgili in Tarragona, where he presently is. Vladimir is an expert on soft matter. In fact, he is a member of the board of the SoftComp network, which is a European network fully dedicated to soft matter. And is the new representative of his university within the ECLT community. So it's a pleasure to welcome him with us. He has been very active in fundraising. He has coordinated many projects in the past, and hope he will with us many additional projects in the future. So with that said, thank you for Vladimir for having accepted our invitations. Please, the floor is yours.
Good afternoon, and thank you very much for invitation. I will present my research project, Enumeration-selection computational strategy for inverse design problems. And before doing that, I will introduce you the university, which is called Universitat Rovira Virgili, and it is a new member of ECLT, and it is situated in Spain, close to Barcelona, and it is on the south of Barcelona, and it is located in several campuses. And the main campus, there are two campuses in Tarragona, and this is the main site. And there are also campuses in Tortosa, Reus, Vila-seca, and Vendrell. So there is a distribution of campuses. That's why it is called, it has this name, Rovira Virgili. And it has also affiliated centers, which are several centers for business and marketing, and Terre de Libre School of Health and Support, and Center for University Studies and Higher Aviation Studies. So it's not only the center for the students, but there is also other schools attached to the university. And it is very active if you see it's a young university, but it is very active in different fields. It has in the size for 2021, it's 14,000 students. This is the size of the university, and it is also shown up in the rankings, in the World University rankings, and it has also a lot of researchers and teaching staff. You see, it's quite a big number of researchers, also international masters students, and lifelong learning students. So there is also for master students, there is a big project. If there are big program in different disciplines, almost covering all type of activities. And it also has this bachelor's, master, doctorate, lifelong learning. So there is those numbers are quite representative. So it's more or less stable, and it has so this number of students is quite big for such young universities. And also there is grants and scholarship students which come every year, so this is quite normal. And now I will talk about my research project. And after this, I will also present you different directions which I'm working in, and what can be also interesting for collaboration, and if you are interested in several projects. So this topic, what is I'm addressing now, is a new topic, and for this topic, I'm focusing on the inverse design problems. And this is a computational strategy. What maybe this is the topic is not new by itself, but in these days it becomes again quite a hot topic because of the rapid advance of the graphical cards and parallel computation. And then those methods, which were very heavy and computational heavy methods, becomes now available. So first of all, I will remind you what are the design problems or inverse search, or inverse problems or design problems. There are different names for this, but the idea is very simple. So usually when you talk about modeling of the system, you first you consider a forward problem. You consider some molecule or some setup of molecular structure with a given molecular structure. Some molecules are composed of atoms, and the structure is already given before you start simulation. Then you set up the force fields, and using physical model, for example, you have you have a model of some molecular dynamics or equations, or some equations for equilibrium state, and then using this physical model you get a microscopic structure, which is here is not shown, but you will get some structure which is a result of the simulation. But for inverse problems, you start with a microscopic structure, and you need to guess or to find the molecular by molecular design. You need to find what is the composition of the molecules which create such microscopic structure. And then you need to get the molecular model or predict the molecular structure. So this is the objective of this approach. Yeah, there's the structure, and the objective of this approach is it can be also formulated in a bit a slightly different way. So the design problems are the optimal design problems that can adapt to find the materials that mimic, adapt, or possess controlled affinity to external conditions. And so we create the external conditions, and the optimal design of the material should adapt to them. So this is a concept of adaptability. And then another concept which was introduced by Jean-Marie Lehn is the concept of dynamic combinatorial chemistry. Then you have molecules or some molecular structures, supramolecular structures, which consist of reversible connections, and or either these molecules with reversible connections or made of conformations of basic elements. And those basic elements can rearrange and dynamically adapt to changes in the environment. So this is a concept of dynamic combinatorial chemistry. And another concept is a virtual combinatorial libraries. So those basic elements or conformations or those reversible connections can be written in the virtual libraries. And reversible and adaptive connections then can be accessed, and you can select in the external field selects from those libraries the material or those molecules which are the most fitted or most adapted to the to those external conditions. And then the conditions may change, but the molecule will also change. So this concept is quite interesting. So this now we can approach this chemical concept from a theoretical point of view. And basically, it's the workflow for design problem is written here. So we have first we start with the target. So we need to we either macroscopic property or we have an external field, and then we need a molecule which has a particular properties or desired properties which fit to this external constraint or external field, or maybe they have certain properties that we want. So this is a target, and then, or we can also call it as a fitting function, or we need to find some macroscopic properties which are already given by the design. And then what we can represent this problem in the way that we are searching for adaptive molecules in a fixed field. So those external constraints in a general may be considered as fields, and the molecule with annealed structure, or maybe with the connections or annealed connections or annealed type, maybe size interaction connections. This monomer it can be of different types, and we search for those for the structure of this monomer as a part of this problem. So this is how it is formulated. And then the solution is the enumeration of all combinations, and either by direct enumeration or using heuristic methods. So that's then the neural network is very good in these problems, and I will explain how they are all connected and how we can do this. So this is a basic idea, and this idea will apply for polymer design problems. And the polymer design is the design goal is to predict the sequence of the polymer. And for example, if it is a linear polymer, it consists of the monomers, and we can predict the sequence of this polymer. And for polymer, there are two basic features. One is a sequence. It's how those monomers are distributed along the chain. And this is a sequence. But for each sequence, we have a huge number of conformations. And the conformations can be translational or rotational, and how those monomers are oriented between each other and in the space. So this is a huge conformational variation, which is conformational or statistical sum, which is sum of all conformations, and that will be here the property which will define the properties of the polymer. And another dimension for the design is the branching, or it can be interconnection between molecules, or it can be a branching. So this molecule can branch, and then additionally to the properties of the monomers, which can be represented by the color, for example, or we can also have a branching. So this is then we need to predict the sequence or structure, and this will be the design goal. It is the simplest design problem for polymers. And how it will be solved, and this is solved in the following way. So we have a molecule with annealed structure, and also we have as a molecule with either structure and also the color. So we don't know the structure and they don't know the color, but the design problem can be described as the fixed field, and which, for example, here in this case, as a spherical field with a hydrophobic and hydrophilic shells, and we need to this polymer to adjust to this field and find the structure which fits the best. So this is how we do. And after this, we can present those polymers either as hydrogen bonds, either hydrophobic, hydrophilic monomers. And actually, this is also as a part. It can be a dynamic or it can be static. And the dynamic, there is a concept of dynamers. Dynamers is dynamic polymers which adapt to external field. And also the water-soluble polymers, which are soluble due to water interaction with hydrogen bonds with water, is also example of such adaptability, because depending on conformation, those hydrogen bonds can be formed or they cannot be formed. And then the external field, maybe this cavity or some dense compact structure, will not allow to form hydrogen bonds, and then those monomers will be not hydrophilic, but they will be hydrophobic. So this is a bit where it comes from. And so this adaptability to the field, there are examples. But I will talk about this problem maybe more in a maybe more theoretical way. So what are the solutions for this inverse problem? So there is an inverse Monte Carlo method, and it's just to solve direct Monte Carlo simulations many times until you reach the desired properties. So this is just direct method, and it's very painful because you need to make a lot of simulations direct. And then there is another method, is neural networks, and to use some good examples. For example, you have a training set which you know how this works, and then you can get a signature of the correct sequence or pattern from those neural networks, and it may predict you the structure. So this is another way. So there are many heuristics. So this is not the result is not guaranteed that it is a correct one, but that you are searching one, but it can explore a parameter space quite efficiently. And another method what I will talk about is the enumeration-selection strategy. Then you directly generate conformations in the graphical cards, and checking on the fly the fitting function. And here what is achieved, and where this speed up is coming from, is that you can do virtually a Monte Carlo simulation, the generation of the conformation on the single thread, not on the single GPU, but on the single thread of the GPU. And then in modern computers, it can be thousands of threads. And each of the simulation can be decoupled and with no communication. So, of course, with a certain price. And I will explain these basic principles of the method. So first of all, the polymers, and they are long polymers. And for long polymers, the main property of those polymers is a large number of conformations. And a large number of conformations of a single molecule. So first we have a sequence, and there's a color of the monomers. But the main problem is to find all those conformations, which are a huge number. And then another thing is that we have a different variability of connection between molecules, and then this is another aspect. So, and to solve this problem, so this what we're facing is this, to find those conformations. And what the method which is closely related to this idea was developed for a very long time ago, but due to computational heaviness, it was not that used. But now it may be it will be one of the way to solve efficiently these problems is that you generate a molecule, and this molecule is can be this linear chain or it can be branch chain already in the field. And the field of other chains is represented in interaction with the other chains is represented by the field. So this is one chain in the field, and the interactions are between molecules are decoupled. So that's why the interaction with many molecules is reduced to generation of the molecule in the field. That's why you are losing correlations between molecules, the movement of the molecules, but and also the fluctuations. Then you have you are getting the minimum of the free energy state. And then the fitting function may be related to the probability of each conformation in a given field. So if we have this field and it is imposed, then we can calculate the probability, for example, of any property. For example, we can do any fitting function based on the probability of each conformation. And then by generating these conformations, we can check this probability and see if this is a good fit or not. And the fields can be very general. So it can be concentration, external fields, and it is general. So, and what is the basis here is that instead of calculation direct interaction between molecules, we calculate interaction of the molecule inside the field. And this is of course, limitation is the mean field. And here we have basic components for numerical implementation is the conformations of the chain. It can be real space conformations, can be conformations from the lattice. And then they have also interaction potentials. And the interaction potentials is a force field, definition how they interact. And then this can be annealed, and then it can be adjusted to the field. And the geometry, for example, we can impose a certain geometry of the system. For example, if we have a field which is cylindrical or spherical symmetry, then we can just put it and only consider those molecules which follow this geometry. And this simplify a lot to solving the problem. So, and then the fundamental obstacle for parallelization of simulations is in general, as you consider molecular dynamics or Monte Carlo, is what is called Amanda law. So it's a fraction of the sequential code, which is with respect to the fraction of parallel code. So here is a number of cores, and then you see the speed up of, okay, maybe it's a bit outdated, but the data, but you see the idea that it's the speed ups is if you have a lot of parallel nodes, of you work with the parallel nodes due to sequential code or due to synchronization between them. This becomes a bottleneck for speed up. So you cannot, if you put a lot of them, then you do not reach the speed up. And of course, it can be improved, but not massively. Here you see the speed up is 6-7 times, but of course you can do 10 times faster than single core. And this is, of course, can be done, but it is not massively parallel. Even if there is parallel, but so you see, if, for example, you reach 95% parallel code, then it can be only maximum 20 times faster. And so this 5% will limit this. And if you do code which is 100% parallel, so it means you use even on GPU, each thread is independent, and of course they will do all the same in the GPU. They need to do the same operation, every clock time. But for example, if we are doing exactly the same, like generating the molecule, or in this, if we generate a molecule, we can do fully parallel generation of the molecule. So if our problem is generation of the molecule and the conformations in the and each thread can do it independently. So basically what we are doing is we are doing small Monte Carlo simulation on each thread. And then we can do thousands of simulations simultaneously, and this give you the collective result. And it's perfectly scalable. So if you have more available cores, or if the GPU becomes with more cores, like 50,000 CUDA cores, then it's scalable. Then its speed up is massive. And then the structure is written here, so it's how it is implemented. And there is if you can work in the global memory, shared memory, there are different realizations. And the speed up, what is considered that it is quite scalable for different GPU. And you see the chain per second can be billions. We can arrive to a generation of billions of chains per second. And that's which is the core of this approach. For example, if we consider building blocks as monomers, and those colors represent interactions, for example, we color them, and this is interactions. Then we consider also self-avoidance. That again, it's not a Gaussian approximation, but we have any type of statistics of the chains, and especially for three-dimensional and with self-avoidance, there is no formula to get the statistical conformations. So then by generating this sampling, we can get the statistical, we can get the conformational, we can get all the conformation. And additionally, we have bonds. The bonds is either can be freely joined, or it can be branching, and then we can also include it. And all those building blocks can be interconnected, or they can be fixed or annealed. For example, we can fix the fraction of hydrophobic blocks, and then the position is annealed. Or we can fix the position and then anneal the number of hydrophobic and hydrophilic blocks. Or we can, this is quite flexible what can be done. And here, what we do, we have fixed composition, adaptive composition, branching, and then there are several examples what can be done. First example, what I will show you is a translocation of a linear polymer chain through a lipid bilayer. So this is example of those how this method works. And for this example, we use the field, and the field is red is monomers, which are called the T monomers, is a hydrophobic monomers. So this can be in the as a planar, as a membrane. For example, we consider a lipid membrane, and blue is dark blue is a hydrophilic part, and it's the head of those lipids, and light blue is the water and maybe the solvent. Then what we have, we can have different configurations, but if we just fix this as a this field, for example, this lipid membrane, we can ask what will be the polymer structure to pass through the membrane, and the fastest, and we can ask find fast and slow sequences. What will be the sequence which will translocate fast or slow? And the fitting function is a mean first escape time, and this mean first escape time is the basically the time to go through the membrane. And another problem that we will also address is the maximum load, but this will be as a maximum load of the object, and I will address it a bit later. So we will design a polymer which will consist of black and white cubes, and those black and white cubes should fit into this field, and in such a way that the translocation through the membrane is a fast or slow. And then what we can do is to adjust, because we have this free energy here, and that's basically this is a one-dimensional problem with the free energy, which depends on the position, and this free energy can be sampled directly in this field. So that's how it is done. And here is the result that we have many combinations. For each of the combination, we generate the full sampling. This means all possible conformations of this polymer, and calculating this first mean escape time. And by doing this, we get, and we can enumerate all possibilities. And this is, of course, not a not a very long polymer, but and for this polymer, we just can enumerate all. And I will tell you later if the polymer is long, and then we cannot do it because, but here is the result. If we have a short polymer, that what we get is the fastest one is when with this hydrophobic block is in the middle, and if we fix, for example, how many hydrophobic blocks we want. For example, we want that it has only one hydrophobic block and all other are hydrophilic. And then what we see, this is the solution, the fastest and slowest. Then we have a half and half, and it's 6-12, it's half and half. Then we have block copolymer is the slowest one, and alternating block with alternating blocks is the fastest one. And among them, this is the best solution. Then we have balanced hydrophobicity, and you see this time is the minimal for 5 and 12. And then we put more hydrophobic or more hydrophilic, the time grows. So that's why the solution is that we have a alternating polymer, and we have a half and half. So that's why this by doing this simulation, and this is a very fast simulation, that we can do those design problems, and we can investigate how it changed when they change chain length. Of course, that with the increasing chain length, the speed of translocation drops exponentially. And what we get here is that, we see here how those solutions, even for different lengths, we still have the same pattern, that the slowest ones are block copolymers with the big blocks, and the fastest one are alternating copolymers. And how it goes, we have a log of this mean time, and this is how we have a fastest and slow. So small blocks means faster, and big blocks slower. So, and then depending on the total chain number and logarithm of this time, and then we have a hydrophobicity, and we can evaluate how it will go. And the same problem was also solved by designing a neural network, and we can compare those predictions with the neural network predictions. And here is how it was done, that a part of the sampling was used as a training set and also validation set. And then the rest was not shown, and then the rest of the of the system was presented to the neural network, found the composition. And that's, of course, if the size of the training set is large, then it's more precise. But here what we see is, again, the prediction of this neural network is here, it's 1 over time. And then then the higher is, if it's on the top, is faster. So here we see that the fastest conformations, they are also have alternating conformations, and the slowest one are blocks. And here the color, so sequence is those numbers, and there's a 612 is a fixed ratio, and the color represent the number of blocks. And so the bit, you see that red is small blocks, and blue is big large blocks, like in block copolymer. And that's why this pattern is also, the neural network has the same prediction. And that the conclusion from here is that exact enumeration, this method is enumerating all possible conformation and predicting, it can be used as a ground truth for neural network. And this is a exact solution. And it's because of its exact solution, it's quite useful. And another example is the localization of the monomers in the chain. And here what we have is a design criteria. What can be, there are 4 possibilities that we have. Design criteria is the fixed central block should be in the hydrophobic core, and then we see the pattern of maximum and minimum. Then another one, then the ends are located on the interface between core and the hydrophilic hydrophobic interface. And C is when the ends are localized in the corona. And then you see then the block copolymers again appear, and tri-block copolymers. And the another one is not fitted, is another type. So, and a hydrophilic, then we have hydrophilic monomers are localized in the corona. Then we have again alternating is a minimum, and maximum is a tri-block copolymer. So this kind of things, how it will choose the pattern. And another example, and this is the last example, is adaptive polymers as a polymers with annealed structure. And here it can be this system with hydrogen bonding. For example, here design criteria is we have the polymer with fixed number of hydrophobic hydrophilic groups, but their position is not fixed. And then the polymer density is what we it's also we have to be found, and also the position on the chain is fixed, and then this can correspond to hydrogen bonding or no hydrogen bonding. And for example, if you have a high polymer density, then you don't have hydrogen bonds, and then the hydrogen bonds will go to the outer layer. And here it's this situation in the spherical symmetrical case that we have these white hydrogen bonds with white monomers outside of the field. And another example is adaptive branching in the field. So we can ask the question, what will happen if the polymer density is affecting the branching, is related to probability of branching. And then what we have is at the center of the globule, if there's hydrophobic blocks go there, then the branching is not happening. It's you can get a dendrimer when the dendrimer is branching field. Branching is has at higher rate outside of the center of the where it is dense, and then we can also reproduce this behavior. And then branching distribution with the polymer density, we can get this result. And so to summarize, I can say that this method is very efficient on modern GPU, then because it doesn't need communication between even GPU cores, and then this allows to generate that you can use it for hybrid methods with neural networks and generate training and validation sets. This is as something and use it as a ground truth or to validate the results, because what you get from this method are the exact results, not just a prediction of optimal structure, but you get exact results. And also another example is that this is quite interesting, that this method is basically you can run Monte Carlo simulation on a single thread of the GPU. And this is, of course, it's a generation of the chain. It's very simple, but you can run thousands of simulations simultaneously in one single GPU. This open door for this combination of different methods with optimization, search, heuristic methods with a solid validation of the result with the exact results. So this maybe the topic I may finish here, and this work was done with Yachong Guo, who is working in Nanjing University in China, and Marco Werner is now he is a group leader in Leibniz Institute for Polymer Science in Germany. And yeah, we have a collaboration with Sergei Pogodin. He's my former PhD students, and also funding from Spanish university, for Spanish ministry. So thank you for your attention.
Okay, thank you, Vladimir. Thank you a lot. So this is a virtual clap on behalf of the whole community and the audience. So are there any questions? I have many questions myself, but I would like to ask if there are questions from the audience. Any questions? Yes, John, please.
All right, can you hear me?
Yes.
Yes, yes.
Thanks for a great fluent talk. My specific question relates to the development of these approaches when you compare it with the specific topic of RNA folding, which I've been involved with. And I'm just wondering about the transfer of ideas that have led to this area. The dynamic combinatorial libraries were investigated in RNA in connection with multiple folding and induced.
Yeah. So maybe we did not look.
So the question, that's the question. Is how you see the development of this area and the algorithms involved in relation to RNA.
So I'm not a specialist in this field of RNA folding, but what I see that it is maybe very relevant, because you have kind of two types of monomers. They are zipped, unzipped, and then you can also consider this. And what we did not do it, which was the simplest case, but I think it's possible to go in this direction and predict structure of this RNA folding. Yes. Because here you just generate
areas that inverse folding algorithms have been developed for, in particular, for secondary structure, but I think also these pseudo-knotted structures based on structural properties of the interactions, which allow you to use dynamic programming type methods. So it's an additional tool in the arsenal of inverse folding to use effectively inverse methods associated with forward methods.
Yeah, I think
that's just one thing that might be of interest to talk about further.
Yes, I think it will be what we need maybe to look in this direction also, but because it looks possible, yes, yeah, but we need to see this.
I'm also intrigued to find out about the machinery and the power consumption of the GPUs in connection with this, but I'll ask that later when given the.
Yeah, good.
There is a question by Maria. Maria, please.
Okay, thank you. Thank you for the very interesting talk and also very clear explanation with visuals. I was just wondering if this methodology, in particular regarding path formation, might be applied, for example, to micro-robots self-organization. So like, for example, swarms which are moving to create a pattern, sorry.
Yeah, so there is an analogy between path and this, or diffusion and a polymer chain. So this is the exact analogy. So diffusion equation and that's how this conformation of the chain. So this can be applied. Yes, how this random walk, because what is the basis of this is a random walk and with a non-intersection with this and 3 dimensions. So that's maybe very similar.
Thank you.
Other questions? I have 2 questions, Vladimir. One is a technical questions, and another one is some sort of perspective questions, question along the same line as John's. The technical question is the following, because of course, even in polymers, especially in polymers, there is not a one-to-one correspondence between the sequence and the structure. So there is a huge degeneracy. You mentioned this. So I'm not sure, how do you cope with this? Because I didn't get how you managed to cope with this this problem.
We solve directly many simulations until so it's just that solving direct problem to find inverse problem. Yes, this is how it. I think this.
Yes, but to a given structure, you have many possible sequence that they can.
Yeah. So the sequence, yes, and then this sequence should fit, and then what you need to get this design parameter or design. Requirement. For example, what in one was a time of translocation. Then we know that the sequence is we can calculate the energy of the monomer of the given conformation on different positions, and then from here you get the free energy, and then from this free energy you get it time. Translocation time. So this is how it's done. It's the same as you do in a simulation. So here it's that you have a field, and it's a field representation. So if you have a field and a sequence, or sequence is with many conformations, and then for each sequence you can calculate an average of any property in this field. So this is the idea how it is done.
Okay. Okay, thank you. So the other question, which is along the same line as John's, because it would be nice to, one of the open problems in protein folding, for example, is the inverse problem, in which you have given a structure, how do you predict the sequence?
Yeah.
And of course, this is a major bottlenecks in which, including the fact that there is not a one-to-one correspondence, but did you ever, consider, in applying this method to that? Because this is, there have been many attempts and many methods, but none of them.
For protein folding, what I think the main bottleneck is that they are not equilibrium structures. What you are getting is they can be stuck in some conformation, and this is very difficult to get all those conformations which are not equilibrium, but they are kind of, there's a lot of states which are not maybe the minimum of the free energy. That's why I think it's a bit, and also the interactions are very, they can be also secondary structure, ternary structure, and everything is influence one on another. So I think protein folding in very difficult problem. So for in general.
Yes, I know.
That's why I would not start with this.
Okay.
It's good to have, but it's very hard. Yeah.
Okay. Okay, thank you. Any other questions for Vladimir? Oh.
Yeah, if there is no questions, I can show you.
No, John is another question. Please,
Okay.
John.
Yeah, I just have two small things. One is you showed the mean field idea with the polymer in its mean field environment, and I'm wondering whether you've considered the step where the actual mean field environment, also which you can calculate from the individual polymer simulations as well. Whether you can actually solve problems where the mean field itself is also adapting, so that
yes, I see. Yes, so what's a fixed field? What you mean? There is a fixed field, and if the polymer is adapted to this, it also affects the field. So there is a self-consistency should be in the system. Yes. And is the method what we use? It's the main method. It has also a possibility to update the field, but then if you can update the field after you find some properties, and that will be possible. But then you kill parallelization. It's affect parallelization because then you have update the field.
So you have to lump it into a block.
Yes.
Yeah, because then this is when you what we do is adapting the molecule to the field, and this you don't need any communication between them. But once you have all conformations, you can calculate the mean field. But then this step, you need information from all threads, and then this to calculate the average. Yes. That's why at this stage you have the synchronization, and then you need it's possible, and then this penalize the parallelization. But that there are methods that you can update the field after maybe 100 steps. So for that, and then you have this self-consistency problem. Yes, you can do this.
Okay, so just one technical thing about GPU usage is I've not used GPUs for doing parallel computation, but other sort of custom devices, FPGA devices, and things. And I'm just interested in about how things work with respect to if you're using the GPU in this sort of mode where you're doing massive amounts of computation really in parallel, sort of maximum output, what the heating and what sort of hardware requirements do you actually need to run this sort of a simulation?
I think the main limitation for it is now is the number of cores and also the shared memory. If you can store these conformations in the memory.
But if you use the GPUs where every computational possibility is being sort of driven at maximum capacity, because your computation is really exploiting the hardware resources, you're using heaps and heaps of power, and it's also hot, so you have to use a special type of GPU that can withstand this pressure.
No, I think we mean the temperature. It was maybe in the beginning one of the students was burned one GPU. This is possible, yes. But I think that modern there is also they have quite a good balance of the temperature balance. So it's even at work at.
Are you using large computer center GPUs or sort of?
No, this is what you can, it depends, because what you need is one GPU with a lot of cores and memory. So this is what you need. And then they are, of course, you can go to computer center, but then you will have more GPUs, but they are all like more or less the same. So you can buy the 300 RTX 3090, yes, and this is already has 24 gigabyte of memory and a lot of cores, like more than 10,000 cores.
Mm-hmm.
It's already you can have it at home, like a game in computer, and it's already 10,000 cores. So it's quite good. Yeah, and the maximum I think I have now 90 or some 90,000, but those are very expensive ones. Yes, you can go, but they also cost a lot. Yes.
Okay, thank you.
So that's, and the number of cores grow. That's why you can have more and more possibilities. Yes.
The other questions? Yes, I see. Johannes, please.
Yes, I have a question regarding also GPU computing. First of all, of course, also thank you for your very interesting talk. What you just say is the speed up of using GPUs in comparison to a multi-core computer.
Yes.
What you estimate the speed up in comparison?
Yeah. So this is usually very difficult to compare like this, because if you compare with single core, it's not fair, because
yes, of course,
single core is maybe fast, and for example, we have a measure which is what was also designed by Marco Werner, and that's what he suggested to do like this: that you have cores multiplied by megahertz, because this also give megahertz, the clock speed is quite important. And on the other side, yes, this measures how many cores, and this is a single core, or then you have less, and then you can calculate the time, for example, how many chains per second you can generate, as a function of course multiplied by megahertz.
I see. Okay, thank you very much.
This is maybe more. Otherwise, if this clock speed is not the same, so of course not fair comparison. Yeah?
Okay. So if you speak of threads in the GPU computing, you think of multi-cores also on the GPU.
Yes. If you have this is in one GPU, we do it on one GPU. Oh, but if you have several GPU, this is okay. But then you need to communicate between them. But they can generate different parts of the sampling. Yes.
Okay.
Can do it. Yes.
Okay. Thank you.
Yeah.
Okay.
And you see here the time in seconds, for example, for GPU, and this means you generate all conformations, all possible conformations. And for the chain length 64, it takes not all, but as you have 10 to power 6 conformations, you get in 3 seconds. You get 64.
Okay.
Thanks. So that's why. To have a good sampling for a neural network, this method it can be quite good. Yes, even if you go for very long polymers, and you can have billions of conformations.
Okay.
Okay. So John, you still have a question, or was the previous one? Okay.
Sorry, I didn't lower my hand, but I could have another question, but.
No, I was just wondering if okay, was the previous one? So Vladimir, you wanted to show us something.
Maybe I can show you other topics just very briefly. That so that we have work. So my main directions as lipid membranes in interaction with nanoparticles, and this was done quite extensively with many interactions. Another topic is the nanostructured surfaces and the modeling of interaction of cells and proteins sitting on nanostructured surfaces. And I will show you some examples. And another is a parallel algorithms GPU for image analysis and also database analysis. And it's also, I will show you what is this. So this nanoparticles, and we have several works, how those nanoparticles cross lipid bilayers and also different objects like carbon nanotubes, polymers. And here we have this mean field approach. Then we have this, we can test with the model what will be the energy barriers and how different objects interact. And another topic is the nanostructured surfaces, which was initiated by Elena Ivanova in Australia. It's my collaborator, experimentalist. And she discovered the antibacterial effect of nanostructured surfaces, which are composed of those pillars or spikes. And they are found on the insect wings. For example, dragonflies' wings or cicada wings, they have those protrusions or those spikes. And on those spikes, you may have, if bacteria are attached to those spikes or arrive to the surface, it is ruptured by mechanical interaction. And this was mimicking, and in the black silicon is one of those materials, and then this bactericidal activity of different effects now and then what we have there is a lot of groups working on this, and they are confirming.
Somialo, can you move the mic?
Yeah.
Yes, thank you.
So, and there are different fibers, different types of nanostructures, and also eyes of the insect. They also have those structures. And there is now, this field is growing very fast. So and what we did also, the structural parameters, which have those properties. And here on the right are the structural parameters in the nature, and in the nature. On the left is a nature, and on the right is a experimental. And then what you see that nature has a very narrow parameter space and height, spacing, tip diameter, and where those nanostructures are situated. And for experimental, there are different types also, and they are mimicking these objects. So this is what if you are interested, I have this type. And another one is to analyze databases also with accelerated analytics using graphical cards and big data solution for environment. And maybe we last year we created a spin-off company dedicated to C topic, and here it's the objective is to collect heterogeneous data and analyze it for prediction. And here what we have is the data which is collected, and then it is presented as a tensor and in the form of a tensor, and already with a structured form. And this tensor is perfect structure for neural network for analysis. And then this analysis can be presented for different users in different forms and as a form of analysis. And for example, this is a graphical interface that can be done. This is what we see how the regress of the seagrass and we see the zones where it regress more and less, and then we can control it. And also we are testing close to Venice, and there are several setups there, so it's quite interesting. And another topic what I don't have the slides is to apply the similar structure to agriculture, and for agriculture we submitted a project on which has the similar idea that we have a lot of cameras which take data, maybe edge device which can analyze already the data, and then this data can be processed and make a prediction, for example, if the quality is good or not and how to improve it. So, and here it is also connected with blockchain technology, and this is also quite interesting application when you can have a traceability of all these operations, and then you can even say not only to trace and not only record and trace, but you can also create a community which will use this data and contribute with the digital trust. So this is, I think, very fascinating. So this is kind of things.
Thank you. Thank you very much. I think this is very interesting. In fact, you know, I will get in touch with you soon on the project with these Dutch people. You know, hopefully we will manage to get in, you know, we are already in touch with them. So let's, you know, we will be working on that. Okay. So thank you very much for joining us, Vladimir. It was a pleasure to have you with us. And I'm sure that there will be many interactions within the community with John and all the other people, with the Rudy and other people that are in the networks. And so next week we will have another seminar, you know, right, Julia?
Nathaniel Virgo.
Yes, so you have received a calendar of the seminars which are already scheduled, and we will have more in the future. So please stay tuned, and until that time, you know, have a nice weekend. Thank you, Julia, for hosting us, and goodbye, everyone. Thank you, Vladimir.